for this particular session, we will be covering alkenes and alkynes reactions. And in order for you to get more context of this, it is highly recommended that you must have also seen the intro on organic reactions, which includes words like addition, elimination, substitution, nucleophiles, electrophiles, radicals, and all this chaos right here. If not yet, then I suggest you watch this first. But if you have already done so, let's proceed here. Now, every once in a while, in order for us to completely know what's going on, we also need to draw the proper arrows or pushing arrows to show how our electrons and bonds move. I will only be using this right now in our introduction and not anymore later because it will consume too much time. But hopefully, by doing this, it will empower us, allow us to know what changes have really happened after the reaction. Alright, let's first start with the idea that since I have an alkene here, a double bond, is more electron rich than a normal single bond. And that means that if it is electron rich, most likely we can declare that our alkene is more or less a nucleophile. And thus, being electron rich, it must find an area in the reagent XY that is electron poor. In other words, something that is towards the positive side, which of course is the letter X. In that case, we can imagine that, first of all, we can get this bond and then imagine that this would belong to one of the two carbons holding it. Oh, by the way, the name of the carbons that hold a double bond are vinylic carbons. So take note of that. And let's say that I have this double bond. I'm gonna give this pi bond to this vinylic carbon. And then continuing from that, imagine that these electrons that I've given to this vinylic carbon, in turn, this carbon gives to this X. Which makes sense because if this is the carbon which has a lot of electrons, this is the atom which contains few electrons or is electron poor, they are the perfect match. But also take note that once I form a bond between carbon and X, this X must let go of its original bond to Y. That means that these two electrons will be relinquished by X, given up by X, and will be given instead to Y. After all the explanation I've done, what would happen is that number one, the pi bond would be gone, so we now have a single bond as a result. And now we can see that this carbon has attached itself to our element X, which we can therefore call as our electrophile because X is electron poor. It's positive or it's towards the positive side. And also take note that since I mentioned a while ago that Y has separated from X, you can just imagine that Y is somewhere around our product here, just floating at the background. Also, take note that since my carbon here initially had 4 bonds, and now my carbon here just has 3 bonds, it's as if one of its bonds has been taken away from him, then therefore we can imagine that this carbon lacks an electron and would have a charge of positive. And this would suggest what would happen next, because now I have a negative charged Y, and this remaining vinylic carbon a while ago turns into, all of a sudden, a positively charged carbon. Just to be clear, we call positively charged carbons as carbocations. So right now, you can just imagine that my carbocation right here and my negative Y right here, which we can see they have opposite charges, are a perfect match. So you can imagine that Y would be giving out one of its electron pairs to this carbon, effectively bonding carbon here, the carbocation and Y, and when they bond, their charges cancel out. And so if that happens, then our ultimate product would be like this. So again, remember, the double bond is now a single bond. And then a while ago, I already showed you that one of my carbons is already attached to X. And now, on top of that, we already see that our Y is also attached to the other carbon, like so. And so, this is the complete final product. Now, what I want us to do is to compare. And in order to do that, I need to erase all of the mess I made here. I want us to compare the appearance of our reactant versus the appearance of the product. What changes happen from here to here? We can find very obvious changes. Like, for example, we clearly see that the double bond has been converted to a single bond. That means that for most reactions of alkenes and alkynes, you should always take note to remove one of the pi bonds. So in that case, if I remove a pi bond from a double bond, it will become a single bond. What else? Obviously, our original reagent was XY, and you can see that in our product here, X and Y have been separated. So we must know that our reagent is supposed to be reagent is supposed to be split into two. Then, when we split our reagents into two, we had to attach them separately to both vinylic carbons. So the last step is actually to attach our reagents to our two vinylic or double bond holding carbons. And always remember these three steps because we will do this again and again and again. Alright. Oh, and by the way, since what happened was I have one alkene and one reagent, so those are technically two things. At the end of the reaction, they combine to become one product. This is an addition reaction. And since a while ago, what we see was that uh, our double bond, if you remember, initially attacked the electrophile, then therefore, this reaction is electrophilic. So the reaction mechanism is electrophilic addition. Therefore, that is going to be the cornerstone of all of our reactions, and we're gonna again do these steps again and again and again. Alright? Again, let me repeat. 1. If I have a double bond, it will become single. And then, whatever reagent I have, I'm going to split it into two. So, if for example, we have the reagent AB, it will be split into A and B. And then, I'm going to attach them separately to my two vinylic carbons. And we will do this pretty much for all the reactions below. Let's start with 1. When we have hydrogenation, it means that you add hydrogen. No wonder your reagent is H2. First of all, remember that the first thing or the easiest thing to do is to change the double bond into a single bond. And then the next thing you do is you split H into 2. And of course, if you split H2 into 2, then obviously you get just simply 2 pieces of H. And then what we're going to do is we're going to add each hydrogen to each vinylic carbon separately. And therefore, your product would have something like this. Now, you start with an alkene, and after hydrogenation, you end up with this one. It's just a single bond, right? So that means the product of hydrogenating an alkene is just an alkane. Next, if I have the process of halogenation, halogen, it means that I'm using a halogen reagent like X2. This can be specified as a specific reagent or halogen. Usually, the halogens that we use for alkenes are chlorine and bromine. So this can be Cl2 or Br2, depending on the scenario. So if I have X2, I know that I can split it into simply two molecules of X. As always, the first thing to do is to convert the double bond to a single bond and then add these two things separately. I add one X here and then I add X to the other. And since I have two halogens attached to my product, I can call it a dihalide. Di means two, right? So two halogens. Also, we can further specify our product and call it a vicinal dihalide. When we say vicinal, it means that I have two things that are beside each other. So it is legitimate to call this a vicinal dihalide because my two halogens anyway are attached to the two vinylic carbons, and it is true that these two carbons are beside each other. That is the meaning of vicinal, beside each other. Then, hydrohalogenation means a combination of hydrogen and halogen. So we have there the reagent HX. And when we can split HX into two, of course, one would have to be H, the other would have to be X. As always, I convert the double bond to a single bond. I add the first letter to the first vinylic carbon. I add the second one to the second vinylic carbon. And in the case of hydrohalogenation, you can see that in our product here, I only have a single X. So I cannot call it a dihalide. So I'll just call it a simple halide because there's only one. Or a simple alkyl halide is the product of hydrohalogenation. Hydration means the addition of water, which you can guess from the prefix hydrate means water. And in this case, water is not the same as the first three in that now you recognize since water is HOH, you're gonna have to double check that you're gonna split it properly. It's actually easy. I mean, if you know that this is the structure of water, whether you erase this bond or the other, you will get two things, one molecule of H and another molecule of HO or OH. So that means water can be split into one H and one OH. So, as always, you convert the double bond to a single bond. Then you add the first one to the one vinylic carbon. So I add the H here. And then this other one, the OH, I add to the other. And all of a sudden, I produce an organic compound that contains the functional group OH. At this point, most of you should already be familiar that organic compounds with OH are called alcohols. So the product of hydration of alkenes is actually an alcohol. Also, let me kind of erase some of the details here. I want to clarify something. In practice sets or quiz questions, it is very likely that you don't just see these reagents on their own. For example, you should know that in hydrogenation, our hydrogen is always assisted by metal catalysts like palladium. But do not include palladium in your product because since it's a catalyst, its job is only to make the reaction faster. But that doesn't necessarily mean you're gonna have to attach palladium in the actual product. Okay? Also, for example, halogenation, sometimes you can use solvents like DCM, and the purpose of a solvent is just to serve as the medium where the reaction takes place. So that doesn't mean that you're gonna add the DCM into the final product. Or for hydrogenation, the usual solvent for this one is an ether. So again, just like DCM, it's just a medium. That's not something that we add. Also, for hydration, when we use water as a reagent, it won't work alone, so we also need a catalyst here. Usually, you need a catalyst like sulfuric acid. Sometimes, a question in the exam or in the test may not state the entire sulfuric acid, but instead may opt to use just the simple formula H plus for a proton. Because we should already know at this point, proton donors are also acids. So this is like their indication sometimes that you have an acid catalyst. We have more. And hopefully at this point, we can already simplify this. Hopefully, when you saw the first four reactions, you already recognized that every single time we erase the double bond and convert it to a single bond. So why not just do that shortcut? It's gonna happen again and again and again, right? So like, let me just fast forward. Let's just convert all double bonds into single bonds because it's pretty much standard as well as this one. Now all we need to do is to problematize what should I attach. For the case of number 5, your reagent is a combination actually of a halogen reagent and water. And in this case, you have to take note that what you will be getting from this combination is a single halogen and a single OH group. Therefore, these are the two things you add. One carbon gets the X, one carbon gets the OH. That's why the product here is called a halohydrin. Because halogen, we have a halogen here, and then hydrin is like hydroxyl group is also present in this product. So again, we call our final product here a halohydrin. 6, this lacks one word. It should be addition of. Of course, we know organic compounds, ROH, are called alcohols. So now, what do I get if I add an alcohol? Let's say that I have the bonds for an alcohol, ROH, and of course, what we know is that in our reagent here, we have to split this into two. Now, we have to be specific here. It's gonna give us a different answer if I erase the bond between R and O and if I erase the bond between O and H. So which is the proper bond to erase? Remember that between R, or carbon, and H, carbon is fairly more electronegative. So you can imagine that this carbon is not gonna give up so easily on the oxygen. Whereas since hydrogen is really less electronegative than the other atoms, it's like it doesn't care. The hydrogen is gonna say, I don't care about my electrons, go get it if you want. In short, this is the bond that we break. So that means that you can split ROH into one molecule of H and one molecule of RO. Or better written as OR, because anyway, it's the oxygen that we should attach first, not the R. And so, as usual, I attach one here and then the other to the next vinylic carbon. And now, look at the format that I have. Let's say that I group this under one group R. And then I have here R, then O, then R. That's an ROR, right? And we should know at this point ROR is the type formula for an ether. So therefore, if I add an alcohol to an alkene, my product is an ether. Next, we have something called mild oxidation. Take note that in this case, if I say mild oxidation, we will use potassium permanganate, but in basic medium. To denote that we have basic medium or alkaline medium, we usually write this OH minus, because from your Gen Chem knowledge, you should already know that bases, based on one of the definitions that we use, donate OH groups. So this is important because in another recording, I will explain something called strong oxidation that instead uses KMNO4 but in acidic medium. So that's entirely different. So this is important. You should take note of this. Now, what do I get? So this is gonna be a long story short kind of explanation because if I'm gonna explain all the steps, there are a lot of arrows to consider. So just take note that if I have KMNO4 in presence of base, all I will do is I will extract two pieces of OH from that. And that means these two vinylic carbons in the product will have one piece of OH each. And that would be the product. Remember a while ago I told you if I have something with two exact substituents and they are attached at the same, or not really the same, adjacent carbons, we call that vicinal. Then notice we also have the same case. Two exact same functional groups attached to two adjacent carbons. So it is proper to use once again the word vicinal here. But it's not anymore a dihalide, right? Because we didn't attach halogens. We attached OHs, alcohols, right? And the name of an alcohol with two OHs is usually the shortcut word diol. Two alcohols. So the product that we produce is a vicinal diol. But do you also know that the word vicinal diol has a synonym? Vicinal diols are also called glycols. And you may need this definition, especially that in medicine, some glycols are poisonous. Next, epoxidation with hydration. It is actually two steps. Epoxidation is the first reaction, which is this first arrow. And hydration, as from the name itself, as it suggests, is addition of water. So let's first focus on the first word, epoxidation. So first, we should be noted that when we say epoxide, an epoxide looks something like this, like a triangle, like we call it cyclopropane in organic chemistry, but one is oxygen. I mean, one atom is oxygen. And so, I want us to focus first on the reagent for epoxidation. You see, the reagent here is the general format's RCOOOH. And that's not really a typo. It's really three oxygens. As you know, if I have RCOOH, we call that a carboxylic acid. But this one is one oxygen excess, and you call these types of acids as peroxy acids. And the idea is that extra oxygen of a peroxy acid as compared to our carboxylic acid is actually the only oxygen that you're gonna attach to my alkene. So if, for example, I have the double bond, I know that it's gonna be a single bond right here. What I'm gonna do is I'm gonna put that single oxygen and I'm gonna link the two vinylic carbons together. And well, doesn't this look pretty much the same as this? So this is actually the epoxide already at this state. Okay? By the way, the most commonly mentioned peroxy acid in textbooks is the reagent MCPBA. Though I will not anymore mention the exact meaning of MCPBA. We should just be aware that this is used for epoxidation. Then, finally, if we add water, one thing that you should know is that, number one, the epoxide ring would actually open. When I mean open, it means that one of the two bonds here is gonna get broken. One will remain. So let's say that I'm gonna break this bond. This will remain. So that means that this carbon is still gonna hold that oxygen. But as for this carbon, it's gonna be a carbocation. So let's get to work. We know that water, we already discussed this a while ago, when split gives you one H and one OH. The H is going to be positive, the OH is going to be negative. So I think it's better matched if I have the negative going to my positive. So let's attach the OH here. So of course, if I do that, this charge is going to be removed. And then obviously the other H here is gonna have to go to this oxygen, which makes sense because this oxygen is rich in electrons. My hydrogen here is poor in electrons, so they're the perfect match. But guess what? Despite all these colors, what we actually produced is a compound with two OHs beside each other, like exactly this one. In fact, that means that my final product for epoxidation plus hydration is actually also a glycol. So both 7 and 8 are methods for producing glycols or vicinal diols. So these are the reactions that I need to cover without any other complicated things or rearrangements or multiple products. And of course, different references, different degrees, different programs from different schools may use different textbooks that have different sets of reactions for alkenes. So you may see that if you're from a different school and you watch this, you might notice that some reactions here have different names in your book. Some in your book I haven't mentioned. Some that are in my slides or in my discussion are not found in your book because many textbooks vary in the specific reactions that they have. So you have to give room for that variety. And as for me, this is what I will stop with for now. Next up, I will discuss some special cases for alkenes wherein we actually have multiple products, which is not as straightforward as the reactions that I have shown you here.